Okay. In the last class, we gave a problem. I mean, we said that x is a random variable which is Poisson distributed, and it takes values. It is a discrete random variable. It takes values like x equal to either 0 or 1 or 2 dot 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 dot. Okay. And the corresponding probabilities is given by like p, if p equal to, I mean for x equal to k, the corresponding probability will be given by e to the power minus a and a to the power k divided by factorial k, where a is a parameter. We ask you to find out the mean and variance, okay? Or rather we ask you to find out E of x, expected value of x, and expected value of x square. Okay, and if you know expected value of x square and if you know the mean, obviously you can find out the variance. Okay, that was a question. A is called a parameter, so we say that x is a Poisson distributed random variable with parameter a. Okay, can you tell us what is the function of this factor e to the power minus a? Actually, if you just consider this part e to the power k by factorial k, okay, this will correspond for various k's. If you take their values and add them, this gives rise to an exponential series. In fact, we should have this thing. This must be equal to 1, right, because total probability is 1. Now, because of this factor, this equality will be satisfied. This we can see easily. Okay. If you put that expression, take this out, k equal to 0 to infinity, and you have got a to the power k divided by factorial k. Now, this is nothing but e to the power a. This is the exponential series. E to the power a when expanded gives you this. So, you have e to the power minus a into e to the power a is equal to 1. So, just to make this equal to 1, this factor has been added, right, introduced. Anyway, this is just a side issue. We have to now find out the mean of x, that is E of x and E of x square. Okay. To do that, we consider this exponential series. E to the power a, which I have just a while back stated, is equal to a to the power k divided by factorial k, k is 0 to infinity, okay, which is equal to 1 plus a square by factorial 2 plus dot 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 plus a to the power k by factorial k plus dot 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 dot, right. I now differentiate these left hand side and also right hand side with respect to a once, and then again one more time, that is twice. So, first if I differentiate LHS and RHS with respect to a, this will give rise to this side as before e to the power a, and this side we have got 1 plus 2 into a by factorial 2 plus dot 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 plus k into e to the power k minus 1 by factorial k dot 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 dot, which in fact you can write as, if you take a 1 by a out, you can write it as k a to the power k divided by factorial k. Okay. Sorry. This should not be this is from 1. For k equal to 1, we have got 1 cancelling and a to the power 1 and that a and a cancel. So, you get 1 and likewise. So, the summation is from k equal to 1 up to infinity this. So, e to the power a is equal to this. This is one identity which I need, I will be using later. So, as I move to the next page, I rewrite this. Okay. Okay. So, what we have just now seen is this, e to the power a is nothing but, I mean one can always also write like this. Okay. If we differentiate it again, this is one result. Okay. And if I differentiate this again with respect to a, left hand side I get e to the power a as before. Okay. Well, I am not differentiating this, I am sorry. Let us take down that series again, e to the power a that was written as e to the power k by factorial k. Okay. And k equal to 1 to k equal to 0 to infinity. We have differentiated it once, we got this. If we differentiate this twice, what do we get? Okay. I mean, it is better that we expand this series term by term. This 1 plus a plus a square by factorial 2. You can have one more term like a to the power 3 by factorial 3 plus dot 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 plus a to the power k by factorial k plus dot 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 dot. If you differentiate it once, you get 1 here, then 2 into a by factorial 2, 3 into a by factorial a square by factorial 3 and likewise. If you differentiate again, out of this you get 0, here you get 2 into 1 divided by factorial 2, here 3 into 2 into 1 into a by factorial 3 and likewise. Here in the general term will be k into k minus 1 a to the power k minus 2 by factorial k. Okay. So, if I say differentiate with respect to a twice, this gives rise to again e to the power a on this side. On this side k into k minus 1 you can put 1 by a square here. So, that you get a to the power k divided by factorial k, and k should be equal to 1 to infinity. You can easily verify this, put k equal to 1, obviously this term becomes 0 because k minus 1 is 0. Okay. And then k equal to 2 onwards, if you put k equal to 2, 2 into 1, okay, a square cancels, 2 into 1 by factorial 2 which you get out of this, and then for k equal to 3, 4 onwards you get the corresponding terms. Okay. Now, I got two expressions, one is this, another is this. Let me go to the next page, write them and then get into the expressions for mean and variance. Okay. So, we have obtained these two expressions, one is e to the power a is equal to 1 by a okay, another is equal to 1 by a square k into k minus 1 a to the power k by factorial k. Okay. Now the question is, what is expected value of x? X takes the value 0, 1, 2, 3 and likewise. So, expected value will be k times p x equal to k and summation k equal to 0 to infinity. Now, you know k equal to 0 case can be ignored, is because you are multiplying by 0. Okay. So, I start this summation with k equal to 1, okay. And we know the probability also. So, this becomes equal to k into, we have already seen what is the probability, e to the power minus a will go out, okay, and a to the power k by factorial k equal to 1 to infinity. Okay. Now, what is this part? What is this part? From here you can see that this is nothing but this, okay. This part is nothing but this part, which means this is equal to a times e to the power a, right. So, you have got e to the power minus a into e to the power a, which is equal to a. So, expected value of x here is a, okay. And now, we go to the other one, what is the expected value of x square. Okay. Instead of moving to the next page, I erase this part here. Okay. So, what is expected value of x squared now? Once again, it is nothing but this, sorry, this would be k square this, okay, and k is taking value. We can start with 1 directly, because k equal to 0 means this term will be 0, this is finite and this is 0. So, we ignore k equal to 0 case from k equal to 1 to infinity, okay, and we know the probability. So, e to the power minus a comes out of the summation k equal to 1 to infinity, okay, and then you have got k square into a to the power k divided by factorial k. What is this? This is not, this is coming out of this expression, okay, out of this expression this is coming, but how? You can see one thing, if you take this expression, if I write on this side from here, you break it up as k square minus k. So, one term you get 1 by a square k square a to the power k by factorial k, another term you get minus 1 by a square k a to the power k by factorial k, right. This part we have already seen what it is a times e to the power a. So, this becomes 1 by a square summation k square a to the power k by factorial k as before, minus this part as I said just now a into to the power a. So, it becomes e to the power a divided by a. Okay. And this is equal to e to the power a. So, what is this quantity? This quantity is appearing here. What is this quantity? You take this to the left hand side, e to the power a is common. Okay. Let me write it here. So, that means what is this quantity? There is a question, right. So, this is equal to this will be equal to a square times, and e to the power a is common. So, you can as well push a e to the power minus a here. Okay. You take this quantity to the left hand side, e to the power a is common. So, bring a to the power minus a on this side. Okay. On the left hand side, 1 by a square multiplying 1 plus 1 by a. Okay. So, what is good then? Get then out of this. Let us again revise. We had this summation, then we broke it as like this, 1 by a square, okay, k square and this, then minus 1 by a square and this, and k a to the power k by factorial k, that was equal to e to the power a by a, e to the power a into a. Okay. So, you get e to the power a by a, this moves to the left hand side. So, e to the power a is common, that goes to the right hand side. So, you have got this term and this is equal to this, which is nothing but a into 1 plus a. Okay. So, this is it. This is nothing but then a square plus a. Okay. And we already have seen what is a. A is nothing but e of x. Okay. And then what is variance? Variance is e of x square minus e of x whole square, which is a square. So, variance sigma square, which is equal to minus E x whole square, this will be equal to A. So, for a Poisson distributed random variable with parameter A, it is very interesting that its mean and variance both are equal to A. Okay. This is a very interesting exercise. Okay. So, we now move to another very interesting topic, which is called moments. Moments associated with one random variable x. Okay. Moments. X random variable with probability density p x. Then nth order moments. There are various definition of various types of moments. So, let us just define them. N is an integer, n could be 1, n could be 0, it could be 1, 2, 3 and like that. So, the usual definition of moment, which is actually called just moment m n nth order moment is nothing but expected value of x to the power n, which is nothing but this. Okay. So, you can see what is m 0? M 0 is just integral of p x dx, which is equal to 1. What is m 1? M 1 is x p x dx integral, which is mean mu, and likewise. Then sometimes some other definitions also are used, like this is moment, there is something called central moment, this is moment, this is called moment. Then there is something called central moment. Here central moments we define as say V n, which is nothing but E of x minus mu, mu is the mean of x, or mu is equal to m 1, which is the mean actually of x. So, instead of taking x to the power n, you take the deviation x minus mu, okay, raise it to the power n, take its expected value, that is V n, which actually is nothing but this. Okay. Then instead of taking x or x minus u, sometimes we take their mod values, okay, and those mod, I mean if I put a mod here, with a mod here, mod x or mod x, or a mod here, then those are called absolute moments, that is absolute moments. Okay. Now, I mean out of this usually the moment and the other one, that is generalized moment, not generalized moment, the central moment, which actually does not take x, but rather the deviation of x from its mean mu. I mean only these two are most commonly used. So, let us consider a relation between them. Say first you see what is V n. V n we have said is nothing but E x minus mu whole to the power n. Okay. Now, this is a binomial series, this is a binomial, you can expand it rather you can expand it in a binomial series, and then it becomes n c k okay. And now using the linearity of expectation operator, apply this E over x to the power k, and E x to the power k as we know is nothing but the kth order moment m k. So, you get this relation. This is sorry. Okay. This is a relation between the central moment, nth order central moment, and the general the usual moments. Okay. We can have a reverse relation also, which I consider next. We have seen M n is nothing but okay. This we can always write as plus mu whole to the power n, right, and then expand it binomially. We have got this expression, sorry, okay. And now apply the expectation operator on this. This will be nothing but the central kth order central moment, and you get this term. V k okay. As a special case, you can see one thing, that what is mu 0 or m 0, both are equal to 1. That is very easy to see, I will not go into it. Then what is m 1? M 1 is, which is nothing but mu. Okay. But what is mu 1? Mu 1 is, sorry, you can put an expectation x minus mu, and obviously x minus mu, its average value is 0. Okay. So, mu 1 is 0. What is mu 2? And this is what we denote by, I mean, this is what we indicate, I mean, we have termed this quantity as the variance sigma square, and we have also seen that if you expand it, you get this m 2 minus actually m 1 square. Okay. M 2 minus m 1 square. Further, if you take mu 3, what is mu 3? Expected value of x minus, sorry, not mu, this is v. Okay. It is just, if you expand it binomially, x cube, expected value of that will give you m 3, then minus 3 x square mu, expected value of x square is m 2. So, minus 3 m 2 mu plus 3 m 1, m 1 and mu are same. So, you get basically this term mu square minus mu cube, and this is nothing but thrice mu cube, because this is nothing, m 1 is equal to mu. So, 3 mu cube minus mu cube. So, which essentially leads to this thing. Similarly, you can express m 3 in terms of v 3. I leave it up to you. This is very simple. Okay. certain things you see, we have just now seen that V 2 is nothing but m 2 minus m 1 square. So, these numbers m 1, m 2 and all that, they are not just some arbitrary numbers, they usually have to satisfy some inequalities. For instance, we know that V 2 is always greater than equal to 0. So, m 2 should be always greater than equal to m 1 square. Similarly, consider this quantity as an example. A is any number and we take the whole square. Okay. Now, for any A, I know this has to be greater than equal to 0, this cannot be negative. But what does it mean? This leads to, if you expand it, x to the power twice n expected value of that, which gives you m 2 n, okay, minus twice a x to the power n expected value of that, which gives you twice a m n plus a square. This is greater than equal to 0 for any a, that is important, which means a minus, you can write like this, whole square plus m 2 n minus m n square greater than equal to 0. Okay. Now, since this is true, this has to be true for any a, this is true also for m n equal to a case, the case where m n equal to a, which means then it is 0. For that case, we have this thing, that m 2 n minus m n square should be greater than equal to 0, that is okay. Okay, now, as an example, we consider the case where x is Gaussian. To make life simple, I assume that it has a mean 0 and variance sigma square. So, it is given p of x is equal to 1 by root 2 pi sigma e to the power minus x square by twice sigma square. So, let us see what is the, what is e to the power x n. I first write down the result. This is equal to 0, we will show how if n is odd, that is sum twice k plus 1. Otherwise, it is equal to 1 times 3, 5 dot 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 up to n minus 1 and sigma square when n is even equal to twice k. Okay. This will show as an example. For that, we consider this integral. What is the value of this integral? You can always take a to b equal to sum 1 by twice sigma square. So, if you make that substitution, e to the power minus x square by twice sigma square, and if we had another 1 by twice root 2 pi sigma here, 1 by root 2 pi sigma, then that would have been 1. So, this is equal to root 2 pi sigma, and sigma we know is 1 by square root 2 a. So, this gives rise to this. This integral is essential for us. Okay. Oh, now before that, we are taking the n equal to even case. Okay. We are taking first n equal to even. I forgot to mention this, n equal to even case. For this, we start with this integral. My point is, if I differentiate both sides with respect to a, say once, what I get from this side? A minus will come, here also a minus will come. If I differentiate again with respect to a, another minus will come, that will make it positive. Here also another minus will come, that will make it positive. So, either both sides have minus or both sides have plus. So, essentially I can retain a plus sign in both cases. If you differentiate it, say k times, okay, where we have seen that n is equal to twice k. If I differentiate k times, what I get? X s to the power, I am not bothered about the sign, because I told you if it is minus here, it is minus here, if it is plus here, it is plus here upon differentiation. So, I can always make a, keep a plus sign here. This is x to the power twice k, because each differentiation brings 1 x square. So, k times means x to the power twice k times this. On this side, what happens here? Square root pi remains as it is. Okay. When you first differentiate it, it is a to the power minus half. Okay. That minus sign I am not bothered, because that will again be taken care of by the sign here. So, half. Okay. Then next time, let us do some rough calculation here actually. Say after differentiating once, we have this thing, it is a to the power minus half. So, this becomes a to the power minus 3 by 2, and half with minus sign comes. This minus sign I am not bothered, 1 by 2. Okay. Next time when I differentiate, maybe it will be better if I erase this here and work out this part on top first. Consider this function. If I differentiate it once, okay, I get minus, though the sign is not important, I told you. When it is minus, I have got a minus sign from the left hand side also, they will cancel. When I have plus sign, on this plus sign here, on the left hand side also I will get a plus sign. So, I am not bothered about sign, both sides can be kept as plus, okay. But still I write 1 by 2 square root pi a to the power 3, right, 3 by 2. Okay. Next time when I differentiate, then I have got 1 by 2 into 3 by 2, okay, it becomes a to the power 5, because after all I have got a to the power minus 3 by 2 here. So, minus 3 by 2 goes, minus minus plus. So, 1 by 2 3 by 2, and this becomes a to the power minus 5 by 2. So, I put it on the square root, so it is over 5, okay, and likewise. So, if you go on differentiating it k times, here I am getting 1 into 3, then 5, 7 like that, and here just 2, 2, 2, 2 k times, okay. And here I have got, if you differentiate it once, that k equal to 1, it is 3. So, twice k plus 1. If you differentiate it twice, it is 5, 2 into 2 plus 1. So, it is always twice k plus 1. Okay. So, what I get then, this quantity 1, 3, 5 dot 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 twice k plus 1 by 2 to the power k square root pi by a to the power twice k plus 1. Okay. Then what happens? 2 k plus 1 is actually n. So, you can just put it 1 3 dot dot 5 up to n. Okay. And now, I replace a by, just a minute. I replace a by as before 1 by 2 sigma square, okay, 1 by 2 sigma square. So, what happens on this side? 1 by 2 sigma square. So, twice sigma square whole to the power 2 k plus 1, that comes here. Okay. So, the right hand side becomes RHS, then becomes this right hand side, it leads to 1 3 dot 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 up to 2 k plus 1 divided by 2 to the power k times two to the power 2 k plus 1 sigma 4 k plus 2 into pi the square root. So, this 2 to the power 2 k, I mean it gives rise to 2 to the power k after square rooting. So, that cancels, a square root 2 is left, a pi is left. Okay. And what happens here? This gives rise to sigma to the power twice k plus 1. Okay. This gives rise to sigma to the power twice k plus 1. Okay. So, what is happening then? Actually, I made a small mistake. This should be minus. This should be minus, because once you differentiate with respect to a once, you get 1 by 2, that is for k equal to 1. So, 2 into 1, 2 minus 1, that is 1. Differentiate again with respect to a. So, now k equal to 2, you get 3. So, 2 into 2 minus 1, not plus. So, it will be minus 1. Okay, that is a small mistake I just noticed. Okay. So, what do you get out of it? 2 to the power k cancels, sigma to the power twice k comes up here, okay, and sigma to the power 2 square root gives rise to sigma, square root pi and a square root 2. So, this will give rise to what? I mean, I can write it like here 1 3 dot 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 twice k minus 1, okay, this 2 to the power k is cancelled, then sigma 2 to the power twice k is equal to n, and this additional term 2 pi and 1 sigma. So, if you take this root 2 pi sigma on this side, okay, on this side as 1 by root 2 pi sigma and a as 1 by 2 sigma square, then that becomes the expected value of x to the power 2 k, which will then be equal to 1 into 3 into dot 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 twice k minus 1 sigma to the power twice k or n, which is the result. Okay. that is the result. So, it is done. I am not writing it formally, I am just saying that this part you bring to the left hand side. So, it becomes 1 by root 2 pi sigma here, which is an A as 1 by 2 sigma square. So, basically this amounts to the expected value of x to the power 2 k, and 2 k is n. So, expected value of x to the power n. So, nth order moment, which is nothing but then 1 into 3 into dot 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 twice k minus 1 sigma to the power n. So, this is for the even case, okay, where n is even, n is twice k. Okay. But when n is odd, then what happens? That is very simple actually. N odd. If n is odd, say n is equal to twice k plus 1, then x to the power n maybe I can make it little simpler. Just consider this p x which is also equal to p minus x. This is important, because Gaussian probability density function is symmetric around its mean, and if you put x equal to minus x, since it is square, there is no change. So, what happens then when n is odd? We have got x to the power n p x dx. So, what I am going to do now is valid not only for Gaussian case, but for any probability density which is symmetric around its mean, for which this relation is valid. Okay. You can break this integral as 0 plus to infinity x to the power n p x dx plus minus infinity to 0 minus for this integral, replace x by minus x. What happens? The limits become, plus infinity, dx is minus dx, so minus will come. This will become plus infinity, this will become 0. So, you reverse it. So, it becomes minus this integral from 0 to infinity. The minus and minus will again make it plus. So, it becomes plus 0 to, I repeat again, if you replace x by minus x. So, dx will give rise to minus dx, a minus will come. Limits will become plus infinity to 0. If you want to make it 0 to infinity, then the integral becomes again negative. So, that another minus sign will come, those two will make it plus. So, plus 0 to infinity x to the power n p x dx. Okay. But if when you put x equal to minus x here, since n is odd, okay, a minus sign will come. So, effectively a minus will come here and we will get a term like this. And do not bother about this 0 minus for the time being, I remove this. Do not bother about this 0 minus or 0 plus, essentially the 0. 0 minus means you are approaching 0 from the left hand side, 0 plus means you are approaching 0 from the right hand side, but essentially the zeros. Okay. So, you have got again a 0 to infinity, as sign as reverse, you get this. And they cancel and you get 0. Okay. So, I suggest then you know try and read this book by Papolis and consider other examples where not only Gaussian, but some other probability densities have been considered and the corresponding mean and corresponding moments, expressions for corresponding moments have been derived. Okay. The very next thing from here is a very important thing called characteristic functions. It is basically related to Fourier transform. Fourier transform of a probability density function is actually a characteristic function. Okay. Now, that I will not start now, but I am just telling a little bit about it. Since Fourier transforms have been very effectively used for carrying out convolution and all that, okay. I mean, you can use this result in the end, where suppose you have got a summation of various random variables, each having its own probability density, and you have to find out the probability density of the resulting sum, which is also a random variable. There this characteristic function is very useful. Also this characteristic function can be used very effectively to calculate moments. The moments which we have just considered, they can be calculated from these characteristic functions very easily. Okay. So, I reserve this for the next class and I stop here today. Okay. So, we have so far covered in this chapter function of random variable, and if y is g x and given the probability density of x, what is the probability density of y? We took several examples. Okay. Then we went into moments. We went into another important thing, that is given a function g x. What is expected value of g x? That is nothing but g x into p x dx integral. Okay. We consider several examples and applications of that. That took us to this notion of moments, not only mean and variance to start with, but more general case of moments. Okay. And from moments we go to characteristic function. That will complete this chapter. Then we will go into what is called joint statistics, that is not only one random variable, but more than one random variable, say two random variables are present and they are related. So, we will be considering things like joint probability density and all that, and do similar exercise. Okay. So, that we, so today we stop here. In the next class, as I said, we will consider these characteristic functions. Thank you. Okay. So, today we consider what we discussed, what we stated last time. We consider a very important topic which is called the characteristic functions. Given a random variable x with probability density p x, what is its characteristic function first? So, given x, random variable p x, probability density, then the characteristic function of x is denoted as phi omega okay, this integral. It is something very similar to Fourier transform. Only thing is that in Fourier transform you have a minus sign here, here you do not have that. Okay. So, phi omega as such is a complex function of omega. Okay, phi omega is a complex function of omega. It is called the characteristic functions, or sometimes the first characteristic functions of the random variable x. Obviously, you can see that we can also write this integral as the expected value of e to the power j omega x, because we have seen given a function g x, its expected value is g x times p x integral. So, that is what is happening here. So, characteristic function is also characteristic function of a random variable x with probability density p x is actually the expected value of the function e to the power j omega x. Okay. Now, as you know using the triangle inequality, we all know that but this is less than equal to, you know this triangle inequality, right? Sum of two sides is greater than equal to sum of third side, third side. That we generalize, and in the case of here it is not discrete sum, but it's a continuous sum. So mod of a summation, mod is equivalent to the length of the overall summation, okay, is less than equal to the individual lengths, okay. So if you apply that, so summation individual magnitudes Px and magnitude of this is 1, so it turns out to be this, and mod of Px and Px they are same because Px is a real and non-negative valued quantity. So this is actually minus infinity to infinity equal to 1. So you see this characteristic function magnitude is upper bounded by 1, okay, and when is it equal to 1? You can see that what is phi 0? Phi 0 is nothing but Px dx, because e to the power j omega x at x equal to 0, at omega equal to 0 is 1, okay. So you have Px dx which is 1, which means phi 0 is real and its value is 1, and the function phi omega, the magnitude of the function phi omega, okay, attains its maximum value of 1 at origin at omega equal to 0, and the magnitude falls after that, okay. So this is the property of the characteristic function. I repeat, phi omega square root 2 pi a y, okay, and of course this is on the positive side u y. Okay. Uy obviously, whether x takes negative or positive, y can always take only positive values. So for any negative y, negative value of y, the corresponding probability is 0 because it just cannot take place. So I stop here today, and we start with the next new topic next time. But if there is any question, I would suggest that you all consider all these theories and try to solve some problems on your own from Papaulis. Also, please go through the worked out examples, because due to time constraint I can take up these worked out examples which are already there for you to read. Okay, so that's all for today. Thank you very much.